Everything in the universe, from galaxies to the atoms in your body, is driven by just a few fundamental forces. It took centuries for physicists to identify these forces, but once identified, they believed that some of these forces were merely different manifestations of the same underlying phenomenon. And once they realized this, some physicists felt that all the forces in nature could be explained by a single theory of everything. Learn more about the fundamental forces of nature and the quest for a grand unified theory and a theory of everything on this episode of Everything Everywhere Daily. This episode is sponsored by Fiji Water. You've probably heard of Fiji Water and have seen it in stores. Well, Fiji Water really is from the islands of Fiji. Drop by drop, Fiji Water is filtered through volcanic rock, 1,600 miles away from the nearest continent and all its pollution, protected and preserved naturally from external elements. In this process, it collects a unique profile of electrolytes and minerals, resulting in more than double the electrolytes as the other top two premium bottled water brands, giving Fiji Water its smooth taste. Fiji Water's electrolytes are 100% natural, and this water even has a perfectly balanced pH of 7.7. I've recently been trying to reduce my consumption of diet soda, and I found Fiji Water to be a great alternative. Visit your local retailer to pick up some Fiji Water today for your next backyard party, beach day, hike, or even your home office. Fiji Water is Earth's finest water. This episode is sponsored by Quince. No one is ever going to confuse me with someone fashionable or trendy. That being said, if I'm going to buy something, I want it to look good, be of high quality, and ideally be affordable. That is where Quince comes in. Quince is the kind of stuff you'll actually wear, like breathable flow-knit polos, crisp cotton shirts, and comfortable lightweight pants. In addition to clothing, they also offer a range of great items for the home and travel. Everything with Quince is half the cost of similar brands. By working directly with top artisans and eliminating the middleman, Quince offers luxury pieces without the markup. And I've told you all about the great items that I've purchased from Quince. From towels to blankets to a duvet, Quince has become my go-to source. Stick to the staples that last with elevated essentials from Quince. Go to quince.com/daily for free shipping on your order and 365-day returns. That's QUINCE.com/daily to get free shipping and 365-day returns. Quince.com/daily. Before we get into the weeds on what the fundamental forces of nature are, I should explain what a fundamental force of nature is. A force is a push or pull that acts on an object, causing it to move, change direction, or deform. And there are many forces in the world. You could push or pull on an object yourself and exert a force on it. A fundamental force is one that cannot be explained as the result of any other force or interaction. It's a basic, irreducible interaction of nature that governs how particles and matter behave. In the case of you pushing an object, you can keep reducing it down to the muscles in your body, then the food you ate, and then the energy in the molecules released by changing molecular bonds. All observed forces in the universe arrive from combinations or manifestations of these fundamental forces. There are generally considered to be four fundamental forces in the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. And I know that some of you right now might be raising a technical objection, but I will be getting to that in a bit. So let's start with gravity, the weakest of the four fundamental forces. It has an infinite range and always exerts an attractive force. It acts between all objects with mass and is responsible for the structure of the universe on large scales, such as the orbit of planets, the behavior of stars, and the formation of galaxies. To appreciate just how weak gravity is, lift your hand in the air. Your arm is able to counteract the entire gravitational pull of the planet Earth. The discovery of gravity as a fundamental force evolved over centuries, culminating in Isaac Newton's groundbreaking work in the 17th century. In the ancient world, philosophers like Aristotle believed that objects moved towards their natural place, such as stones falling towards the earth. And this was a qualitative idea, not a universal or mathematical one. A more scientific approach to gravity began with the work of Galileo Galilei in the early 1600s, who conducted experiments that showed all objects fall at the same rate, regardless of mass, contradicting Aristotle's views. The true formulation of gravity as a universal force came with Isaac Newton. In 1687, he published the Philosophiae Naturalis Principia Mathematica, where he proposed the law of universal gravitation. Newton declared that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Although Newton described how gravity works, he didn't explain what it is. That deeper understanding came with Albert Einstein in 1915, who showed in his general theory of relativity that gravity is the result of the curvature of space-time caused by mass and energy. The second fundamental force is electromagnetism, which is much stronger than gravity and also has an infinite range. It acts between charged particles and is responsible for electricity, magnetism, light, and most of the interactions you encounter daily, like friction and chemical bonding. Opposite charges attract, and like charges repel. The discovery of electromagnetism as a fundamental force unfolded over centuries, beginning with separate observations of electricity and magnetism before their unification in the 19th century. In ancient times, people observed that amber, when rubbed, could attract light objects, which was an early observation of static electricity. Likewise, natural magnets were known for their ability to attract iron. These phenomena were thought to be unrelated until much later. The modern understanding began in the 18th century with scientists like Benjamin Franklin, who experimented with electricity and proposed the concept of electric charge. However, the turning point came in 1820, when Hans Christian Ørsted discovered that a current-carrying wire could deflect a magnetic compass needle. This was the first evidence that electricity and magnetism were connected. This discovery launched a wave of research. André-Marie Ampère soon showed that electric currents produce magnetic fields and formulated mathematical laws describing this relationship. Michael Faraday then discovered electromagnetic induction in 1831, showing that a changing magnetic field could induce an electric current. The unification of these insights came through James Clerk Maxwell, who in the 1860s formulated a complete set of equations, now called Maxwell's equations, that described how electric and magnetic fields are generated and interact. The third fundamental force, the strong nuclear force, is the strongest of the four forces, but acts only over extremely short distances, about the size of an atomic nucleus. It holds protons and neutrons together in the nucleus and binds quarks inside of protons and neutrons. The discovery of the strong nuclear force arose from the mystery of how atomic nuclei stayed together despite the powerful repulsion between positively charged protons. Since like charges repel each other, something stronger than electromagnetism had to be at work inside the nucleus. This problem became evident after the discovery of the atomic nucleus by Ernest Rutherford in 1911. His gold foil experiment showed that atoms have a dense, positively charged core. But if the nucleus was made up only of protons, the repulsive electromagnetic force should blow it apart. Something had to hold it together. In 1932, James Chadwick discovered the neutron, which helped clarify the structure of the nucleus. Physicists now understood that atomic nuclei consisted of protons and neutrons, collectively called nucleons. But the puzzle deepened. Since neutrons carry no charge, their presence didn't explain how they could help bind the nucleus together. To solve this, physicists proposed the existence of a new powerful force which acts only at very short ranges of about a femtometer. In the 1930s, Hideki Yukawa developed the first theoretical model of the strong force. The final of the fundamental forces is the weak nuclear force, which is responsible for radioactive decay and nuclear fusion in stars. It also operates at very short distances and can change one type of subatomic particle into another, such as turning a neutron into a proton during beta decay. The story begins in the early 20th century with the study of beta decay, a type of radioactivity where the nucleus emits an electron or positron. In 1896, Henri Becquerel discovered radioactivity, and soon after, beta radiation was identified as one of its components. But a puzzle emerged. In beta decay, energy and momentum seemed not to be conserved. To resolve this, Wolfgang Pauli proposed in 1930 that an invisible, neutral particle must be escaping along with the electron. He called it a neutron, but it was later renamed the neutrino after James Chadwick discovered the actual neutron in 1932. Enrico Fermi incorporated this idea in 1934 into the first full theory of beta decay, introducing the concept of a new fundamental force, the weak force. Before I mention that some of you may have raised an objection when I said that there were 4 fundamental forces. For the purpose of studying basic physics, 4 are usually given, but in reality, based on our current understanding, there are 3. And this is because it turns out electromagnetism and the weak force are actually the same thing, and they're now known as the electroweak force. The unification of the electromagnetic force and the weak nuclear force into a single force was one of the major breakthroughs in 20th century physics. This discovery came not from a single experiment, but from theoretical insights in the 1960s, followed by key experimental confirmations in the 1980s. The starting point was that both the electromagnetic and weak forces shared some important characteristics. They act on leptons, such as electrons and neutrinos. They obey quantum field theory, and they both are mediated by subatomic particles known as bosons. Photons in the case of electromagnetism, and W and Z bosons for the weak interaction. In 1967 and 1968, Sheldon Glashow, Steven Weinberg, and Abdus Salam independently developed what became known as the electroweak theory. They proposed that at very high energies, electromagnetism and the weak forces are not distinct, but 2 manifestations of a single underlying force. In 1983, the W and Z bosons were directly observed at CERN in Switzerland using the super-proton synchrotron. Their observed properties of mass, charge, and interaction behavior matched the predictions of the electroweak theory almost exactly. So, there are really 3 fundamental forces then. Well, many physicists believe that the electroweak force and the strong nuclear force might also be the same thing. This is a central goal of theoretical physics at the moment and is known as the grand unified theory. After the electroweak unification was confirmed in the 1970s and early 80s, physicists sought a deeper unification that would combine all 3 of the known quantum forces: electromagnetism, the weak force, and the strong force. At extremely high energies, trillions of times higher than those currently achievable by particle accelerators, it is hypothesized that the strong and electroweak forces become indistinguishable and are described by a single force with a unified set of fundamental particles and interactions. So if at some point in the future, physicists can prove the grand unified theory to be accurate, then there would be 2 fundamental forces. So could these 2 forces also be unified? This is known as the theory of everything. Merging gravity with other fundamental forces, however, is extremely difficult because gravity, described by Einstein's general relativity, is a classical theory based on the smooth curvature of space-time, while the other 3 forces are described by quantum field theory, which operates with probabilistic particle interactions. Attempts to quantize gravity leads to mathematical inconsistencies, particularly infinities that render the theory inoperable at extremely high energies. And if you recall my episode on the ultraviolet catastrophe, this type of mathematical problem was how quantum mechanics was initially founded in the first place. Theoretical efforts such as string theory and loop quantum gravity remain unproven. This fundamental incompatibility between quantum mechanics and general relativity remains one of the greatest unresolved challenges in physics. So, depending on what can be proven in the future, there might be 3 or 2 or just 1 fundamental force. Except that might not be true either. Putting aside the unification of forces that I've just discussed, some physicists are proposing that there might be a 5th fundamental force, or maybe even more. In recent years, a team of Hungarian physicists reported evidence for a possible new force-carrying particle they dubbed X17 based on anomalies in the decay of excited beryllium-8 and helium atoms. Some cosmological models propose that dark energy, the mysterious energy driving the universe's accelerated expansion, might be explained by a new long-range force acting on cosmic scales. This force would be extremely weak and could interact with mass or space-time in some novel way. Also, some theories extend general relativity by adding a new force that interacts with matter and gravity. These models predict an extra fifth force that can vary and change with time or environment. So, of the fundamental forces in nature that affects us every day, we're positive that there are at least 4, which is really 3. But it might be 2, or even 1, but could be as many as 5 to 7. Absent a breakthrough in theory, or a major discovery, or the construction of a massive particle accelerator, the ultimate answers to these questions will probably have to wait. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Austin Oakton and Cameron Kiefer. I want to thank everyone who supports the show over on Patreon. Your support helps make this podcast possible. I'd also like to thank all the members of the Everything Everywhere community who are active on the Facebook group and the Discord server. If you'd like to join in the discussion, there are links to both in the show notes. And as always, if you leave a review or send me a boostagram, you too can have it read on the show.